Hello, my name is Scott Grizzard from the University of South Florida. My nameplate is down there. Oh, there it is, because that's where they wanted me to put it. And this is Discrete Mathematics. This is the first lecture for the Discrete Mathematics class, live on Twitch. You may be seeing it later on YouTube, edited and then placed later on YouTube. Couple things. If you are in my class, there are two ways to communicate. There's the Twitch chat. Oh, it's that way, isn't it? Where you can, of course, say things there. And there is also the Discord chat. So if you are in my class and you want to ask questions and you want your privacy protected, please ask them in the Discord chat. And remember that anything you say in Twitch chat over there is public. So anyone from anywhere can see that. Again, private questions, Discord chat. Okay. So, and yes, there's a 30-minute delay for followers on the Discord chat. I'm sorry, not on the Discord chat, on the stream chat, which I did because I don't have a TA today, which brings me to my next thing. If you ask questions, I will, of course, see them in both. But normally I have a TA that will answer your questions. I just don't have one today, because he's doing other things to set up other classes. Hopefully, by next time, by Thursday or by next week, that TA will be in chat and able to answer questions, in chat as we do it. So anyway, and yes, I have all fake fans. No one's actually a fan of mine, right? I have all fake fans. So any questions before we begin? So let me just go off real fast. No, the 30-minute delay is not for the video. The 30-minute delay is you have to follow me and wait 30 minutes for you to be able to speak up in Twitch chat. So it keeps people from rating the chat, from rating my my channel, and then spamming the chat server. But the so no, that's not the 30-minute delay is just to prevent random raiders from being able to spam the chat. Okay, so anyway, the way this works is that we do the lectures, of course, online. You can ask questions. Later, they'll be posted to YouTube. You're not required to attend the lectures live. The only thing that you're required to attend live on this class are the tests. And you do have to attend those lives at the dates provided. We'll start by going over the quiz, and then we'll get into the lecture. Okay. And as I said before, I'm managing without a TA today. So if it's a little rough, I apologize. We'll get TA in here later. So let's begin by looking at this quiz. That's what we'll normally do. And, of course, the first thing I click on is going to have slight technical issues. It's one of those days. There we go. Okay. All right, so the first quiz, a couple of questions. What is your name? What is your quest? What is your favorite color? Yes, the Monty Python reference.
What is your favorite color?
And what was the last math class you took? I assume that we're all on board with those questions. If you had technical issues, again, this is the first quiz. If you have technical issues and things like that, actually, the Proctorio quiz is supposed to be posted one day before the thing. That's a mistake on the front. If you have issues with the quiz, that's fine. It's first day, I'm kind of zen, do this during the first week or two.
Strikes and gutters, ups and downs.
Where we get everything working about it. So yes, but it'll have to wait. So yes, I can set it back up, but it's going to have to wait until after class. Also, if you have not done the first day attendance quiz, that's the one that is called, let me see here. That is the one called the course orientation quiz. Make sure you get that done, because tomorrow morning I am supposed to drop everyone that hasn't done that quiz. So if you go to that, if you make sure that you do the course orientation before tonight, so you don't get dropped. This was the quiz that it was referred to. And if you click on the syllabus button, you actually get a list of all of the things in order when they're due. Okay. So again, let's go back over the quiz. What's your name? All those things. And then what I wanted you to do was simplify without a calculator. So the point of this was to remember that this 1 over 1/2 is the same thing as 1 divided by 1/2, which is, flip the fraction. And you wind up with 2. 2 to the 4th, that's 2 times 2 times 2 times 2, which is 4 times 4, which is 16. And remember this factorial symbol. You probably haven't seen it in a while. That's why we're going over it again. This factorial symbol means multiply all the numbers below. 4 times 3 times 2 times 1 equals, 12 times 2 equals 24. The next one is the binomial, a FOIL. And this is something we're going to get into next time. That's the binomial theorem way to do it. Or you could just, multiply these out, and you get 1 plus 2x plus x squared. You do not get 1 squared plus x squared. You need that term in the middle. Okay, and then, so how do we feel about how do we feel about number, how do we feel here about number, let's see, 5 pole. So how do we feel 1 to 5 about question 3? So when I say that, if you're in Discord, you will actually see the numbers pop up as a poll. So there's a bunch of emote polls. You just tell me 1 to 5 how you feel about that. And that's how I ask, I kind of judge how everything's going, whether or not I should go over a subject again or things like that. So when I say 1 to 5, I'd like to, just fill out the poll. Yeah, 1 is supposed to be, I don't know what the heck that means. And 5 is going to be like, yeah. So just 1 to 5, how do we feel about those? 1 being, I have no idea what you're talking about. 5 being, I'm extremely confident. Would you move on already? So that's kind of the ranking system. That's all it does. Any questions about that one? Yeah, so that factorial symbol was probably forever ago. A lot of people, they're supposed to cover it in pre-calc, and they don't. There's a lot of things that's supposed to be done, and they don't. And as I said before, there's a bunch of people talking about the quiz, whether it was due before or after. It was due before. I will reopen this quiz so that you can do it after. It's the first week. Again, kind of zen about it afterward. There's someone saying that Robert Connolly did. Awesome. I love him. He's probably the person who said, go take Scott for this. Because he hates you and he wants you to have a horrible time. Okay. And then this last one, and this is actually a really important one for us. The question is, if 32 equals 2 to the x, what is x? So this idea about, I keep multiplying 2's until I get that number. And that number here is 5, right? 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32. And this 2 to the power, or you could have just taken you could have just taken the log base 2 of 32, and that's the answer you get. But this idea of 2 to the something is going to be extremely important for us, especially today, because that's how bits work. And that's how counting, that's kind of the place to start counting things. All right, are there any questions about this? 1 to 5, how do we feel about that last one? Let me do a little 5 poll again. There we go. So you just click on the emote that corresponds to the thing. 5 poll is a little slow. I don't know if that's what's going on with 5 poll. What's going on with the poll bot? We were having a lot of trouble with it yesterday. So apparently there's a backup bot on here too that I can use. I haven't gotten it. Let me see. Is there a way to... there it went. I don't know why it wasn't filling up the screen before. Okay. The poll is in Discord. So you have to be in the Discord You have to be in the Discord chat in order to see the polls. Okay. So let's talk about... okay, well, I just minimized the chat. That was good of me. Oh, I need a TA. I need a TA. Okay, there we go. All right, so hopefully you all watched the introduction video and all of those things. So let's talk about what we want to talk about today. Are there any questions about the quiz? Kind of a simple quiz. As we go on, the quiz reviews are going to take more and more of our time, which is fine. And it's really important to me. This class is terminal in the sense that I can slow down. If we don't make every topic in the book, it'll hurt my feelings, but it won't actually hurt your ability to do, I'll make sure that I cover the very, very core stuff. Maybe we won't get to some of the fun stuff. It'll hurt my feelings, but that's it. It's not like, the calc sequence where you have to cover this in calc 1 or else, you're not going to be able to do anything in calc 2. So let me just say something very quickly about that. If you've looked on the syllabus, okay. Besides the fact that it's 24 pages, which is way too long, you will see in here the kind of design of the class. And then you will see kind of the overall objectives, and then you'll see the things that I actually want you to remember 10 years from now. So there are a bunch of these skills and a bunch of mathematics that you need in order to do IT and cybersecurity, or at least in order to do them well. And one of the major, and that's the material to be covered in this class. And I want you to be able, when you're done with this class, I want you to be able to move on with the rest of the program, knowing the mathematical things that you need to know. So we need to know a lot of number theory, some clockwork arithmetic. We got to go through the binomial theorem about 8 different times. We need to know how to do proofs. We need to know how to do proofs by contradiction, induction, recursion, those sorts of things. But then there's other stuff that the computer science guys don't cover that we're going to cover, like finite state automata, because you actually need that, and it's not covered in your class later on, but you need that really in order to get good at regular expressions. So we are going to cover that. Then we're going to be doing, and then we're going to be doing coding, as you know. And that coding, our big goal is to connect the math to the code. Because the kind of overarching theme of this whole class is that math is code and code is math. So we're going to start that process, and that's going to be especially kicking into next time when we actually start looking at scripts and how to count how many times things iterate. The language that we're using for this class is PHP because it's very flexible. It will do command line things, so you can actually write programs in PHP. It's not calculus with programming. We're talking about discrete structures. So we're talking about things like sets, counting sets, logic, those sorts of things. So, and then the code relates to that. We're using PHP because, it's easy. It's used a lot. If you are going into IT, at some point you will be required to set up a LAMP server, a Linux, Apache, PHP, and MySQL. And you're going to be stuck with it. It's actually useful. We're actually doing something that's useful and part of the class. So that's why I chose PHP. I also chose PHP because the programming class is using Java and they're similar, as opposed to Python, which is just totally different. Syntax is different. Okay. So that's enough about kind of what we're doing here. We'll talk about it some more. Why am I chosen to pick this class? I have a master's in math. I have a master's in econ from way back. I also spent 10, 12 years as an IT professional. So I kind of know what I'm doing when it comes to IT stuff. And that's why they pegged me to do it. So if you think that I'm doing math that you're never going to see again, there may be a reason why I included the math in the course. I'm just saying. Okay, so let's see. Let's go back to the screen. All right, so today what we want to do is we want to go over sets, list, and counting. It's kind of the beginning. Okay. And we're going to start by talking about how many messages can be encoded in a bit. So if I have a switch on or off, how many messages can I send you? You know, Paul Revere sitting on top of the lighthouse. Of course, he's not the one at the lighthouse. If he's only got one lantern, if the unnamed guy in Longfellow's poem only has one lantern, and he can signal what? He can signal that the British are coming or that they're not coming, right? If they're not coming, there's no lantern shining. If they are coming, there is a lantern shining, right? The British are coming. That's one lantern. So how many messages can I encode with one bit? So a bit Okay, so if I've got one lantern, it's either there or it isn't. It's 2, right? 0, the British are not coming. 1, the British are coming. Of course, that's not how the poem goes, right? The poem goes 1 if by land and 2 if by sea. So, how many messages can we encode with 2 bits? Well, 0, 0, no lantern showing. 0, 1. Brits are coming by land. 1, 1. Brits coming by sea. But I've got another thing I can encode, right? I can encode a 4th message. You know, there's another message that can be encoded here. So with 2 bits, I get 4 messages. Well, what about with 3 bits? Oops. Oh, forgot 1, 0, 0. Sorry. I want to keep the pattern going. So this was what I get for 2 bits. And then if I add another bit, I double my capacity. Right? I've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? How do we feel about that? 1 to 5. So now I can do 8. Okay. All right. And every time I do this, every time I double the number, every time I add a bit, I double my capacity. That's supposed to be 2 to the 4. All right, and n bits carry 2 to the n messages. Okay. Are there any questions about that? Yeah, it doubles every time. Let me ask you this. How many messages could be carried with 0 bits? Yeah, 1. Right? Can't distinguish anything. I've got no bits. Right? We just say the British aren't coming. But it's a message, right? There's nothing encoded in it. There's only one possible message. I can't make any distinguishable messages because I don't have any bits. So it just carries the one message. Nothing. All right. Now there's a question about 2 to the 8th being a byte. And that's a very good question. So if you ever pull up an ASCII table, it's got ads all over it. I'm sorry I didn't make it so that it didn't have these ads. So these people are getting, more than they're worth, more than they paid for. If I have this in here, if I pull up an ASCII table and I get something like this, right? I've got notice that I've got 127, but 0 is also a message. So I have 128 messages. How many bits does it take to send those 128 messages? I've got 128 distinguishable messages. So what's the answer? Well, let's see. We already said that 2 to the... We already did 2 to the 5th, so now we double it again, and then we do times 2, and it turns out that there it is, right? We need 7 bits to send those 128 messages, as you guys have said. And then I have a byte. I have a bit in the front, and that makes that standard 8-bit. That's why 8 bits is a byte, because you've got 127, 128 different messages, plus the thing that says whether or not you're dealing with an ASCII character or whatever. So that's kind of the code system that we're using. And then if you use UTF-8, of course, that's 8 bits. Now, there's something else up here. Notice here, of course, this is the 127, this is the octal code, but notice that there's this interesting way of dealing with these things called hexadecimals. And this is a side thing, but it's interesting to note where hexadecimals come from. If I wanted to count 16 different messages, right? That's 4 bits of information. How could I do that? I'm spelling all of this wrong, aren't I? So the question is, how can I do 4 bits numerically? Am I still on the web page? Yes, thank you. How can I represent 4 bits numerically? Well, the answer is hexadecimal. Okay? What I do is I use the numbers 0 through 9 and A through F. Okay? So in order to count in hexadecimal, I would do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. What am I doing wrong? 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. What am I screwing up? Somebody yell at me. This happens often because my brain is just not in it. Oh, duh. I put 4 on the first one. There we go. There we go. My first column had 5 items. Okay. Duh. Thank you, everyone. 0 to 4 needed to be there. All right, so I want to represent these 16 different items, and then if I want to if I wanted to do 8 bits, I could represent those as 2 decimal. By a pair of hexadecimals. And that's what we call hexadecimal notation. So again, that's an aside. And that's where it comes from. It comes from the math. It comes from this 2 to the n notation, 2 to the n, the idea. How do we feel about that? So just, 1 to 5, how do we feel about the idea that that's why we use hexadecimals? Okay. Let me see if there are any questions here. How do I want you to submit notes? You can submit them, you can type them, you can write them on paper, you can write them on OneNote, however you want to do it, they just can't be mine. And there is a nice little way to do that. Let me check the other one. Yep, okay. So it looks like we're good. Okay. Are there any other questions? Yes, you can copy what is written in your old format. I'd like a little bit of extension, but that's okay. All right, so we've talked about counting messages, and we've talked about the encoding in bits. Let's talk about sets. Which is entirely inappropriate, right? If you say it too quickly. But we will talk about it. So, let's talk about sets. Now, for our purposes, a set is our primitive. It's the thing by which we define everything else. All right? But from an intuitive notion, we're just going to call sets a container, a collection of objects. And for the moment, we're going to stick only with finite objects. Okay? So for our purposes, a set is just a collection of objects, and for the moment, we only want to talk about finite objects. Okay, so there's a couple sets. Let's give an example. So we have the set that is the collection 0, 1, 2. Okay, this is a set. A, B. The set containing the symbols A and B is a set. This is the set containing the numbers 1, 0, 1, and 2. Now, it's important to note. Oh, and here's a set also. This is the empty set. Okay. So we have a couple of examples here. I've got a finite set here. I've got a two-letter set. Some things about sets. One, contents are distinguishable. Repeats do not matter. What I mean by this is that this should be EG, isn't it? The sets A equals the set A. These are the exact same thing, right? Two items of A, as long as I can't distinguish. Since I cannot distinguish that A from that A, this is just a set A. Okay? Everyone on board with that? Okay. 2, order does not matter. In other words, the set AB equals the set BA. Okay? So these are the two things right here. Some things about sets. Contents are distinguishable. Okay? So if I've got two items in a set, they're not the same item. All right? If I've got two things that look like the same thing in a set, it's actually just one thing. All right? So a set is something like a deck of cards in the sense that as long as they're unordered. And number 2, order doesn't matter. So the set AB is the same thing as the set BA. How do we feel about those things? 1 to 5. All right. Okay. I see some things about the connection to Twitch. If it gets blurry, if you hit refresh, it usually will reset the thing. So on Twitch, if you hit refresh, it often will fix the problem. Okay. All right. So some other things we want about sets. All right. Again, for the moment, we're only sticking to finite things. Okay. Let me just check the questions here. Class notes. Okay. And then we have this property of sets that we call cardinality. So this means definition. The cardinality of a set of a finite set is the number of elements in the set. Okay. So, for example, all right, okay. So how do we feel about that little bit? Oops, I lost my thing. Okay. And yes, duplicates are ignored in sets. So let me give you an example of that. This right here, AA, is the same thing as this, which is the same thing, which is 1. Because this actually only has one distinguishable element in it. So 0, 1, 2, the cardinality of that set is 3. The cardinality of the set, how about, okay, the cardinality of the empty set, what do you think that is? How many items are in the empty set? None. Yes, exactly. Perfect. 0. Now, here's a question for you. What is the cardinality of a set containing the empty set? Yeah. This set, this outer set, has one thing in it. A copy of the empty set. What is this cardinality? Oops, I need one more of these. How many items are in that set? Well, there's 1, 2, 3, 4. There are 4 items in that set. So the cardinality of this set is 1 because it contains a copy of the empty set. The cardinality of this set, of the empty set itself, is 0 because there's nothing in it. That's the definition of the empty set. Okay, so the question is, how could a set contain nothing? Well, because it's a set. It's an empty bag. I can have a purse containing nothing. I've never encountered such a creature, but I'm sure that in some theoretical sense that such a thing could exist. I could have a box with nothing in it. Here's a box with a cloner alliance thing in there. Right, now I've got a box with nothing in it. This is an empty set, in one sense. The contents of this box are empty. Okay. So there's nothing in it. It's an empty set. There's one more property of sets. And that is sets are distinguishable by their contents. In other words, the set itself has no labels. Okay? In other words, if I've got a set containing the numbers 1 and 2, that is identical to every other set that only contains the items 1 and 2. Okay? There's no way to distinguish one box from the other, right? It doesn't matter what, the containers are featureless in a sense. Okay? They're completely distinguishable by the stuff in them. Okay? How do we feel about that, 1 to 5? So sets are completely distinguishable by contents, and I can't spell distinguishable. What that means, this is actually more of a clarification on property 2. So what that means is that the set, this is another way A equals, if big capital A equals 0, 1, and big capital B equals 0, 1, then A is the same thing as B. Okay? So this is saying that I don't care what label you put on the set. A set is only determined by its contents. In a weird way, this would be saying that a box with nothing in it and a bag with nothing in it are the exact same thing. I can't distinguish the box from the bag. I can only look at the contents. Okay. That's a little weird, but okay. Let's keep going. Now, If for every item A, that item is also in B, we say that A is a subset of B, and we write that as such. In Mathese, that looks like this. Okay? Whoa! Symbols! Symbols, symbols, symbols. Evil symbols. Ah, symbols. All right, so this statement right here says if for every item in A, so if for every X, I just instantiated a variable in A, X is in B, then A subset of B. Okay? I don't really care about this for every symbol. I'm putting it up there because it shows up in places. All right? But that means the following. All right. So this for every business. Again, this is kind of silly, but what if I just said for every, that's that little upside down A, item. Well, I wanted to name the item. Okay? I went up to this thing that was in A and I went, what are your pronouns? And it said X. X are its pronouns. So this is a stand-in for objects in A. This says if for any item X in A, that item is also in B, then A is a subset of B. And that's all it means. And we'll come back to it and come back to it and come back to it. I don't like this symbol in class, to use it in class. I'd rather just say for every, but it's up there. It exists, so we might as well say it exists. All right, and this X is just a pronoun for the objects in A. Okay. How do we feel about that? 1 to 5. So, for example, A is a subset of AB. A is a subset of A. Now, what about the empty set? The empty set is a subset of anything. Because look at the definition. For anything inside this thing called the empty set, well, there's nothing in it. Is it the case for that all X in A, all X in the empty set, is that X in that set there, AB? And the answer is yes. And why is the answer yes? Because the statement is vacuous. There's nothing in here. The statement is vacuously true. Is it true that every item in here is also in here? Well, of course, because there's nothing in here. It's a vacuous statement. Okay. Well, let's let A equal the following set. So there's a question for you. How many subsets are there of A? Let's list them. We have the empty set, which is a subset of everything. We have the set A. We have the set B. And we have the set C. And then we have the set AB. We have the set AC. And we have the set BC. I will answer your question. There's a question in chat that's actually a very good one. I will answer it in just a moment. So, back to this question in chat. Didn't you say that the empty set counts toward the cardinality of a set? If the empty set is in everything, does that always mean it always adds? No. This set A does not contain the empty set as an element. Okay? So, this set B equals, if I have a set containing the empty set, this right here contains the empty set as an element. But this set C here does not. And that is a very good question. So if I take a box, let's say I've got an empty box. This right here will be our empty box, this old GoPro case. And let's make the box actually empty. Oh, this box has got a ton of stuff in it now. Okay, so I have an empty box, and let's say this is an empty box. And I put the empty box in this box, and I close it up. Now the outer box contains one element. It contains an empty box. That's different from a set, right? Now, the empty set is a subset of this set with a battery in it. So I put a battery in the box. Okay? Now, a set containing a battery and the empty set are both subsets of the set containing the battery. Because look at the definition. If for every x in A, x is in B, then A is a subset of B. Okay? Is every item in this empty box also in a box with only one battery in it? Yes. Is the box with only one battery in it? Is it the case that every element in a box with only one battery in it is in a box with only one battery in it? Yes. They're the same thing, but it's true. If I take a box with the stylus and the battery in it, right? A box containing only a stylus is a subset of a box containing both a stylus and a battery. And a box with nothing in it is a subset of a box containing just a battery and the pen. Okay. So now let's go back to this question. How many subsets are there of A? So for how many sets is it the case that this definition is met? And yeah, someone's asked in chat. So the subsets are any possible combinations, and yeah, that's actually connected to a bit. Yes, AB is a subset. It's right there. Okay, how many are there? Let's count them. There's 1, 2, 3, 4, 5, 6, 7, and 8. Why? Why 8? I like that, by the way. In Discord chat, that meme is going in the video when I edit it. Or that GIF. Well, let me ask you this. If I have 4 elements, how many subsets? No, it's not 8. Look at every set here where I had only 3 elements and then add one more possibility each time, right? So here I've got the empty set. So this was the one of the 5 elements, of the 3 elements. Okay. Now, I enumerated the 8 elements, the 8 subsets. It's not that there are 8 elements, there are 8 subsets. Now, let's add the D item to it, right? I now have another item. So let's add it in to each one. So if I add a D here, I can add a D here. 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 And I can add a D here. So I've doubled the number of subsets by adding one more element. Where have we seen that before? Exactly. Subsets and bits are related. The number of subsets and the number of bits are related. That's kind of cool. So, if A equals N, then the number of subsets of A is 2 to the N. For this reason, we denote the power set. So, definition. I'm not going to make it to list. That's okay. Okay. So 2 to the A is the symbol we use to denote a power set. Now, there are other symbols around. Like they've got some books have this curly P thing. And there are P of A is also a symbol. I don't like these. This is the kind of new standard. But sometimes you see these in other words, in other books. So, example, let A equal the set AB, then 2 to the A equals the set containing the empty set, the set of A, the set B, and the set AB. How do we feel about that, 1 to 5? Okay. Yeah. I feel pi about that, right? Okay. All right. So what we've gone over is we've gone over sets. We've begun to count sets. Okay. There is a basic rule called the rule of multiplication. And I'm going to mention this because this is what we're going to talk about. I didn't make it to lists. Let's make it to lists. I'll do lists, and then I'll do von Neumann. Von Neumann takes about 10 minutes. So let me define what a list is, and then we'll get to the rule of multiplication later. Okay. So for our purposes, a list is basically an array in PHP or programming, okay? So, for example, the list, and note the different notation. The list A, B, A, C is different than the list A, B, C, which is different from the list B, A, C. So order matters, and duplicates are allowed. This little thing is called an angle brace, or an angle thing. All right. Okay. So that's what a list is. That's what we're going to do next time. We're going to do one more thing today, and that is we're going to define the natural numbers. So sit back. Yeah, man, we're going to define some natural numbers here, baby. All right? All right, we're going to define natural numbers in terms of sets. And this is actually going to be kind of important for us later, though not as it is. But, let's sit back and let's do a little Zen math. Yeah, let's do some math, man. Let's define the natural numbers. This is von Neumann's construction. All right. All right. We called the empty set. It's a set with nothing in it. I'm going to call that 0. Okay? So I have a bag. Box, nothing in it. That's the number 0. How do we feel about that one? Now, I'm going to define the number 1 as the set containing the empty set. So that makes this the set containing the number 0. All right, well, what did I need for this? Let's write down some axioms. And I don't want you to think like axioms are things from I'm constructing the natural numbers. So I'm constructing the set 0, 1, 2, da, 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 da. I'm constructing our first infinite set. So my first axiom. There exists a set called the empty set. If two sets exist, then their union exists. So these are my axioms. First, that the empty set exists. Second, if two sets exist, then their union exists. There exists a set containing all the stuff in both. With 3, for any set that exists, there is a set containing only that set. All right. So those are my axioms. The empty sets exist. If two sets exist, then their union, then there's a set containing all of the stuff inside of it. And for any set that exists, there exists a set containing only that set. In other words, if A exists, then there exists a set containing just A. And don't let these scare you. But the point here is to show you how little I need to make the natural numbers work. So 0 is the set, defined as the empty set. The number 1 is defined as a set containing the empty set, which means that number 1, is my head in the way? Okay. I'm looking at the chat and not at the screen that shows me what I'm supposed to be looking, what I actually look like. Now, I'm going to find the number 2 as the set containing 0 and 1. In other words, the number 2 is the set containing the empty set and a set containing the empty set. Number 3 is going to be the set 0, 1, and 2, which equals the empty set, the set containing the empty set, and the set containing the empty set and the set containing the empty set. Number 4 equals the set containing 1, 2, and 3. 0, 1, 2, and 3. which I can translate here, but I'm not gonna because I'm done with that. How do we feel about that, right? What's number 5? 5 is the set containing 0, 1, 2, 3, 4. N, then, is the set containing 0, 1, n minus 1. And these dot, dot, dots means pattern continues. Yeah, man! We've now defined the natural numbers in terms of sets. Saying that, okay, why? 0 exists. That's one of my axioms. The empty set exists. 0 exists. 1 exists, right? Because for any set that exists, there is a set containing only that set. So the empty set exists. Therefore, the set containing only the empty set exists. Well, 2 exists because I've got the set containing the empty set exists. The set containing the empty set exists, right? And the empty set exists, and the set containing just the empty set exists. Therefore, their union exists, right? So here, for example, here's how I get this from axioms. 2 equals the set containing the empty set union the set containing the empty set, which gives me a set with 2 elements. So now the cardinality of each, right? The cardinality of each of these elements is the element itself, right? The cardinality of 0 equals the cardinality of the empty set, which is just 0. And the cardinality of 2 equals the cardinality of the set 0, 1. Which equals 2. Moreover, for every element, for every number, right, if k is less than n, that implies that k is an element of n. Also, if k is less than or equal to n, that implies that k is a subset of n. Yeah, man. Okay. So, that's just kind of the cool thing that you can do. This is called the von Neumann. Let me make sure I spelled his name right. I think I spelled his name right. Did I spell his name right? I put it at the top, right? Yeah, that guy. So that's the von Neumann construction of the natural numbers. The natural numbers exist. Now, actually, I haven't said that. There's one step I can't make. I cannot get to infinity using this construction. I can get you to anything, but I can't get you to infinity. And this axiom is going to come back and haunt us a couple times because we want it. We want to be able to talk of things that are an infinite size. Notice here by these axioms, I can define any number, any whole number, but I can't actually define the sets, the set containing every whole number because I can't get there. For any whole number, I can define it, but I can't define the set containing all of the whole numbers. So that's what we're going to do there. That's called the axiom of infinity. And that means that there exists a set that does this. And this is one of the key things that we're going to come back to again and again and again. A lot of times we're going to use it kind of in the background, but it's going to be there, that there is this axiom called infinity. All right. So today we talked about how many messages can be encoded in bits, and how do I count them. We talked about what a set is, and we talked about the cardinality of sets. We did this. We talked about the number of sets. We did not do this yet. And we did not do any of this, but we did this stuff here. So we did do these things. We will pick up with the rule of and next time and do lists. And we will also do, Stop. Okay, so the next time we will get to counting lists, how we count lists, the rule of and, the deck of cards and hands of poker, and the binomial theorem. We may not make it to the binomial theorem yet. Any questions for me? So the lesson will be posted on YouTube. You can also watch it on Twitch before I edit it, so you can replay this whole lesson. And I will reopen the first quiz for everyone, just to make sure we got it. Yes, the YouTube channel, it should be linked in the description on Twitch. If you're not a member of my class, it's linked on the front page in Canvas. But the YouTube will have an edited version of this. There's not a whole lot of editing I'm going to do because it just takes too long. And Premiere Pro was choking this morning on creating things, so I still haven't finished the calculus one. Do we have a quiz on Thursday? Yes, we will. I will have it. I wanted to know how far we got, so that's the first thing I'm going to do is create the quiz for Thursday. And then I should have the so I'll post it in the files on so I will post it right here under quizzes. So that will be this afternoon. That will be posted. And then the actual quiz to take it on Canvas will be, with Proctorial, will be posted probably tomorrow. Okay, so in order to get credit for day one class, you need to go on to the first day attendance is right, here. Is right here. You have to do the course orientation quiz. This is the first day attendance. You need to do this quiz by tonight, the course orientation quiz, or you get dropped. So the fact that you were in chat doesn't actually help. You need to do this quiz. All right. Let's see. Can you see our chats? So that was that one. Let's see. Am I going to accept subs and donations on Twitch? No. I actually don't know what a sub is on Twitch. I know what a donation is, but come on. My discrete class. that got me on this last semester. So they're the ones who talked me into using this. I do post the notes online after. So the notes will be, if you go to files, you go to class notes. This is where I'll post the notes. And I also posted the notes from last semester. So the first class notes you could see were right here. Unfortunately, I wasn't using OneNote at the time, but you could see what I posted there. And you could see that I got farther, but I didn't go as in depth. This year should be better. Hey, it's my second time teaching it. First time teaching it, it wasn't perfect. Let's see. Each number of cassettes. Yes, that's true. That's up to you. I'm not actually smoking the weed on Twitch. I'm just like doing the emote because it's funny. And I think that's it. The quiz will be due so the orientation quiz is due tonight at midnight. 11:59. The quiz for Thursday will be due on Thursday. Is the book truly optional? Yeah. Oh shoot, I forgot to mention. This is chapter 2 in the book. I need to say that. So this right here, this material here, is actually in chapter 2. So there's not a good book that does what we want it to do. All the books that are about this stuff and discrete math are written by mathematicians for computer sciences, and they think a certain way that's different than the way that IT people think. And the math that they need is a little bit different than the math that IT people need. So, there's a lot of overlap, hence we can use the book, but we're going to be jumping all over the place because the book doesn't really fit, and there's not a good book out there that really fits what we want it to do. That was a good question. Is the book truly optional? I recommend getting an older edition of the book. Save your money, because we are not using the online homework for the book. So you don't have to buy some online homework system. When are the quizzes going to be posted? So the new quiz will be posted. Day 1, chapter 2. Yes. What about the quiz that was due at 3:30? I will post it. Are pictures of notes acceptable? Please scan them as a PDF for the love of all that is good. Please scan them into a PDF. If you don't know how to do that, you can use one of the PDF. You can use one of the PDF. Is it okay to have 2 pages front to back of notes, or is one piece of paper? No, it's so a page is 1/2 of a size of a page if you're looking at the rubric. So if I covered this whole sheet with stuff and then that sheet with stuff, that would be 2 pages. Are pictures of notes acceptable? I said that. PDF them, please. Use an app in your phone if you must. Is it only on Amazon? No, you can find that book on eBay too. I'm not going to mention about the person who said something about online. What should you be doing out class? Look at the notes. There's usually links and stuff in there. Also, for the book, you can read the book, but work on that stuff there. Yes, that's a good point to bring up. The book is actually really good if you're looking stuff up for the quizzes. But that's one of the reasons why the edition of the book actually doesn't matter. Quiz 1A will be due tonight after I put it back up. Okay. So that's it for me. Uploading the notes is necessary. It's one of the assignments. Do I teach discrete structures? No. The person who teaches that is actually computer science. I am not. Okay, that's it. Goodbye. Sorry for running a little over, but I did answer questions at the end.